Imagine, if you will, a grand Victorian library in London. I mean, just picture it. Complete silence. Total, utter isolation.
Right, like dust motes floating in the air, no one talking.
Exactly. And according to tech writer Aaron Rose, this is exactly what it feels like inside a Python multiprocessing pipeline.
Yeah, it's an incredibly stark image, but it's accurate.
It really is. Your parallel processes are effectively trapped in their own soundproof locked rooms, right? They're totally unable to see or hear each other. And today, the mission of this deep dive is to figure out how to punch a hole through those walls.
Which is quite the task.
Oh, definitely. We're pulling apart a story from Rose's blog, tech-reader.blog, and it's titled The Secret Life of Python: How to Share Data Between Processes. We're going to decode the mysteries of shared memory.
Specifically, how to get parallel processes to actually talk to each other, without completely destroying your data along the way.
Right. Because whether you are currently trying to scale up a massive data pipeline, or you're just insanely curious about how computers actually juggle multiple tasks at the exact same time without colliding, this deep dive is going to save you hours of debugging headaches.
Oh, absolutely. Countless hours.
So, okay, let's unpack this. We enter Aaron Rose's story inside that grand library setting where we meet two specific characters.
Yeah, we have Margaret, who is this wise, seasoned senior software engineer. She treats code architecture like real craftsmanship.
And then we have Timothy, right?
Exactly. Timothy is her ambitious junior colleague, and he has just built something he's incredibly proud of.
Yeah, he's created what he calls a grandmaster analysis engine.
A very cool name, by the way.
That's for sure. And it's designed to be blindingly fast because, well, he's utilizing 4 separate worker processes to crunch chess moves simultaneously. He's utilizing the full power of his CPU.
Right, but he has hit a wall.
A major wall. He wants a live global high score to display on his main console screen. And the concept is straightforward, right? Every time one of his 4 independent workers finds a winning chess move, it should add a point to this one central total.
I mean, the intention makes perfect sense. You have a team of 4 workers, so you naturally want them to update a single shared scoreboard.
Yeah, but the technical dilemma is that the total just keeps coming back as 0.
Right.
Like, he set up a standard global variable at the top of his Python script, assuming all 4 processes would just continuously add to it.
Which is what anyone would assume, honestly.
Exactly. But his main program is just staring back at him, insisting absolutely nothing has happened. The global score is 0, even though his CPU is running at maximum capacity.
So Margaret has to step in here. She has to explain the harsh physical reality of the parallel universe Timothy just commanded his computer to create.
The locked rooms.
Yes. When you use Python's multiprocessing module, you're not just running multiple functions. You are asking the operating system to spawn entirely new, completely independent environments.
I was trying to visualize this memory separation while reading, and I keep coming back to those locked rooms. Like, multiprocessing is basically like cloning yourself 4 times, right?
Yeah, that's a great way to think about it.
And putting each clone into a completely soundproof, windowless room to do some work. They have their own desk, their own pens, their own paper. They absolutely cannot see each other's notes.
Total isolation.
Right. And if you give them each a whiteboard and say, hey, this is the global score whiteboard, please update it, you haven't actually given them one shared board.
No, you haven't.
Python just dutifully hands a blank copy of that whiteboard to each individual room.
Because to worker A, workers B, C, and D do not even exist. They're operating in complete voids.
Wow. Just total voids.
Yeah, when the operating system allocates memory for a new process, it aggressively protects that memory space from other processes. For security and stability reasons, mostly.
Makes sense.
So, when Timothy created that global variable, Python complied by giving each of the 4 locked rooms its own private, isolated copy of the variable.
Ah, so the workers were indeed finding chess moves and updating their scores.
Exactly. But they were only updating their local versions. The main program, sitting out in the main hallway, never saw a single update.
Leaving Timothy stuck with 4 different scoreboards that he can't even read.
Right, but Margaret tells him there is a way out. She explains that they can build what she calls a wormhole.
A wormhole. I mean, calling it a wormhole sounds almost like sci-fi, but how does that actually translate to raw Python engineering?
So Rose's article highlights 2 specific tools within Python's multiprocessing module designed for this exact rescue mission.
Okay.
They're called value and array. And what these tools do is force the operating system to carve out a tiny, highly specific piece of shared memory. And the crucial distinction is that this shared memory sits entirely outside of those isolated parallel universes.
So going back to our library analogy, it's like installing a single indestructible whiteboard out in the main hallway
Yes, exactly.
and giving each of the locked rooms a special restricted window they can look through to see it.
That captures the architecture perfectly. And so value is used for a single piece of data, like Timothy's high score counter.
Right.
An array is used if you need, like, a fixed size list of data.
You know, as I was reading through how Margaret implements this wormhole, I noticed some very strict rules. Because Python is usually incredibly forgiving, right?
Usually, yes.
Yeah.
Very dynamic.
Yeah, you create a variable and throw whatever you want into it, a number, a string of text, a whole list. Python figures it out dynamically. But to use value or array, you have to use specific typed codes.
You do.
Like Timothy is forced to pass an IA to explicitly declare it as an integer. Because we are dropping down to C-level memory, we completely lose Python's dynamic typing, don't we?
We absolutely do. We lose all the comforts of high-level Python. What's fascinating here is that the reason we lose that flexibility is because standard Python objects carry a massive amount of hidden baggage.
Baggage. Like what?
Well, a simple integer in normal Python isn't just a raw number. It is a complex object wrapped in metadata, reference counts for garbage collection, and, dynamic type definitions.
Right, all the stuff that makes Python so easy to use.
Exactly. But raw system memory, the actual silicon, doesn't understand any of that overhead. It only understands exact bytes.
So you have to explicitly declare your memory footprint. You pass that IS, so the operating system can allocate the precise byte size needed for an integer with no Python metadata attached.
That is the exact mechanism. You are bypassing the internal mechanisms that make Python so easy to read, and you are touching raw system memory.
Wow.
And that also explains the other quirk Timothy runs into. He can't just access the variable directly. He is forced to read or write specifically to a property called .value.
I found that fascinating. The dot value property acts as the translation layer, right? It's like the safety handle on the wormhole that takes that raw C-level byte data and translates it back into a standard object that normal Python code can actually read and display on the screen.
Yeah, exactly. So Timothy implements this setup. He uses value, he sets his type code to integer, he targets the .value property. And initially, it looks like a complete triumph.
Right, because he watches the score climb perfectly to 400.
Yes. All 4 workers are finally looking through their windows and updating that single shared scoreboard in the hallway.
It's a huge victory.
It is.
But then Margaret points out a massive catch.
A really big one, yeah.
The illusion of safety shatters quickly because Timothy had to introduce a lock into his code to make it work. And, this is where I really have to push back on the premise because it feels completely counterintuitive.
How so?
Wait, I thought the whole point of multiprocessing with separate GILs, global interpreter locks, was that we didn't need locks anymore. Why are we suddenly bringing them back?
Yeah, that is the exact trap that catches almost every Python developer when they first begin scaling up their applications.
Really?
Oh, absolutely. We assume that because we bypassed threading and went straight to multiprocessing, we are safe from the miseries of managing locks.
Because the common wisdom is always the GIL prevents 2 Python instructions from executing at the exact same time, so your variables are inherently safe.
Right, but the common wisdom is incomplete. Let's look closely at Margaret's explanation to Timothy. She says the GIL only protects Python's internal soul.
Internal soul. I love that phrasing.
It's great. The GIL is Python's internal traffic cop. It protects the standard Python objects that the interpreter creates and tracks inside those locked rooms. But remember the mechanism we just discussed for the wormhole.
Right. We bypass the interpreter. We drop down to allocate raw C memory directly from the operating system.
Which means the GIL has absolutely no awareness of that memory.
Oh.
Yeah, it cannot lock what it cannot see. The GIL has no jurisdiction out in the shared hallway.
That makes so much sense.
So the very second you build that bridge between the universes and expose that shared C-level whiteboard, you reintroduce the most terrifying concept in parallel programming.
The race condition.
The race condition.
It sounds like a geopolitical thriller, honestly. But it is a silent killer of data integrity. Let's break down exactly how this danger plays out with Timothy's high score at the CPU level, because it's wild.
Sure. So let's imagine worker A and worker B both find a winning chess move at the exact same millisecond.
Okay.
They both look through their wormhole window, at the shared whiteboard.
Okay.
They both read the current score, which is, let's say, currently sitting at 100.
Okay, so the read cycle happens simultaneously. They both hold the number 100 in their local memory.
Right. Next is the compute cycle. Worker A thinks I need to add 1, so my new value is 1 over 1. Worker B, completely independently, thinks I need to add 1, so my new value is 1 over 1.
Uh-oh.
And finally, the write cycle. Worker A reaches out and overwrites the shared board with 1 over 1. A microsecond later, worker B reaches out and overwrites the shared board with 1 over 1.
Leaving the final score at 101. Even though two distinct winning moves were found, the score only went up by 1. The data from worker A was entirely paved over and permanently lost.
Exactly. Because updating a variable isn't one action, it is 3 distinct CPU instructions. Read, compute, write.
Right.
If you don't have a lock-a-literal mechanism that forces the workers to line up, take the key, use the wormhole, and return the key, those 3-step cycles will eventually overlap.
And the workers will override each other.
They will. And the worst part is, it might not happen every time. It might only align perfectly and fail once every 10,000 operations.
Oh, making it an absolute nightmare to replicate and debug.
A total nightmare.
Here's where it gets really interesting. Timothy has this grim realization. He looks at his supposedly elegant code and realizes the trap he has fallen into. By using shared memory to solve his scoreboard problem, he has accidentally resurrected all the terrifying dangers of threading.
Every single one.
He has to manage locks manually, he has to guard against race conditions, and he has to worry about deadlocks, where processes freeze permanently, waiting for a key that never comes. Yet he is still paying the heavy computational cost of running full independent processes.
Yeah, he has essentially inherited the worst aspects of both worlds just to get a live high score.
It is a sobering moment. You realize that forcing the operating system to bend to your will gives your code more power, but it also provides your code with deeply complex new ways to spectacularly destroy itself.
That's the reality of it.
So Timothy is staring at this mess of locks and race conditions. How does a developer actually decide if the headache is worth it? Rose's article breaks this down beautifully into a decision matrix provided by Margaret. Let's walk through these core scenarios.
Let's do it.
If you just have a simple integer counter, like Timothy's high score, Rose points out that value paired with a lock is your best bet.
Right, that covers your basic numeric scoreboards or status flags. And if you need to scale that up to, say, a top 10 leaderboard or a specific matrix of numbers, you simply swap value out for an array.
Okay.
But, crucially, you must keep that lock to protect the array slots from overlapping writes.
Which makes sense for raw numbers.
Yeah.
But what if the data is complex? Say you need to share a nested dictionary or a list that constantly grows and shrinks dynamically. You can't use fixed C memory arrays for a dynamic list because you have to declare the exact byte size up front.
No, you can't.
For complex data, Margaret suggests using a tool called a manager. But she includes a massive warning label about its speed.
Yeah, the performance penalty of a manager is severe. And looking at the mechanism explains why.
How so?
A manager doesn't just allocate a block of memory. It actually spawns a completely hidden, separate server process running in the background, solely to manage your dictionary.
Wait, really? So it's acting like an internal database server just for your script?
Exactly that. Well, wait, let's rephrase. Think of it like sending an email to a separate department. When worker A wants to update the dictionary, it can't just change the memory.
Okay.
It has to serialize the Python dictionary into bytes, a process called pickling. Send those bytes over an internal communication pipe, wait for the hidden server to deserialize the data, make the update, serialize a response, and then send it back.
Oh, wow.
Yeah. You gain all the flexibility of normal Python dictionaries, but the latency of packing and unpacking that data over internal pipes is astronomical compared to just reading local memory.
If the wormhole is dangerous and the manager is brutally slow, what is the preferred alternative? Margaret's ultimate piece of advice for Timothy is to abandon the shared whiteboard entirely and stay on the conveyor belt.
The conveyor belt.
And by that, she means relying on a queue.
Right. A queue in Python's multiprocessing module fundamentally changes the architecture. It handles all of the locking, all of the synchronization, invisibly under the hood. You don't manage any keys.
The conveyor belt analogy works so well here. Instead of a shared whiteboard that everyone is fighting over and over writing, you just have a safe, orderly, one-way belt moving boxes of data out of the locked rooms.
Exactly.
Worker A finds a chess move, drops the result in a box, and puts it on the belt. The main program simply stands at the end of the belt and takes the boxes off one by one, adding up the score locally. It is clean, it is organized, and it fundamentally avoids the race condition entirely.
It is the architectural gold standard for inter-process communication. But Margaret leaves Timothy with one final, crucial concept regarding the wormhole, and it is what she calls the shared memory tax.
The shared memory tag.
Yeah. Every single time a worker process interacts with shared memory, you pay a tax in computational overhead.
Because grabbing a lock isn't free.
Far from it. When a worker has to wait for a lock, the CPU performs a context switch. It pauses execution, checks flag statuses at the kernel level, reaches out through the translation layer to raw memory, releases the lock, and signals the operating system to wake up the next process.
That's a lot of steps.
It is. If you put that sequence inside your main heavy data processing loops, say, updating the shared memory 1,000 times a second, you will completely destroy the speed benefits you gained by using multiprocessing in the first place.
You essentially build a multi-million-dollar Formula One car, but force it to stop and pay at a toll booth every 10 feet. You ruin the momentum.
Exactly. So the developer has to architect around the tax, pass the heavy data, the complex payloads, over the safe conveyor belt of the queue, reserve the shared memory wormhole strictly for the tiny, infrequent status updates.
Like a live high score that only needs to refresh a few times a second.
Sora.
So, to bring this all together for you listening, the main takeaway from Aaron Rose's exploration of the Grand Victorian Library is this. Python grants you the incredible power to build wormholes between parallel universes, but power should not dictate architecture.
No, it shouldn't.
Your default instinct should always be the safety and order of the conveyor belt. Rely on queues. Save the shared memory for those rare moments when you absolutely, positively need a global state, and you are fully prepared to manage the locks and pay the performance tax.
It demands an intense level of code craftsmanship. But analyzing this entire ecosystem, the friction of the locks, the race conditions, the heavy tax of serialization and shared memory, if we connect this to the bigger picture, it raises a much larger question about where computing is heading.
How so? What is the bigger picture here?
Well, if bridging the gap between isolated memory spaces is this fraught with peril and performance bottlenecks on a simple 4-core machine, it makes you wonder about the future of ultra-fast parallel computing.
Right, because processors are only getting more cores.
Exactly. As we push towards systems with hundreds or even thousands of processing cores, the sheer friction of managing locks will mathematically overwhelm the system. It suggests that the future of software might force us to abandon the concept of shared state entirely.
Wow, abandon it entirely.
Yeah, we may have to stop trying to maintain global scoreboards altogether and move purely to isolated independent actors that only communicate by passing messages. It implies a profound, fundamental shift in how we will have to architect the reality of tomorrow's software.
The idea that the global scoreboard won't just be difficult, but will eventually become physically obsolete due to the physics of computing. A fascinating, slightly terrifying place to leave it. Thank you so much for joining us in the library today to decode this. Until next time, keep your processes safe, mind your locks, and we will catch you on the next deep dive.
Thank you for having me. And remember to respect the conveyor belt.